Let's talk about how agents are built today. I'm glossing over a lot of difficult parts, but at a very high level, an agent can be thought of as a harness around some sort of frontier model. Um, so this is how you build your agent. This is a convenient description for me because I want to talk about some of the pain points you're going to run into when you're working with frontier models. There's all the standard headaches of security, compliance, and privacy that are exacerbated when you're in an enterprise setting. You also have to deal with this treadmill where every 6 months to 2 years, the current version of the model that you've built and tested your agent on is now no longer available in the API. And if you're doing really generic things, you can generally assume that any incremental version of the model will be better. They always improve at the benchmarks. But the second you're doing something niche, it's kind of a crapshoot. Like the new model may be better, it may not be. And you're going to have to spend a bunch of time fielding questions from your customers about, hey, I used to do this thing that used to work. Why is that broken now? Cost is often an issue, especially if you're dealing with large volumes of data. Very common when you're doing multimodal applications. Latency, also a big concern. We have a couple of companies that we work with that are building devices, wearables and whatnot. For them, latency is a huge issue, but there's also a really cool project called Magnitude, which uses vision AI to automate UI testing. And for them, using one of those big models means that your tests take hours to run as opposed to minutes. It sucks. But really the biggest problem, I think, is customizability. Using a frontier model is a great way to prototype and get something out there that works. But if you're if it's a core part of your product, you probably want to differentiate from your customers. You want to be able to give feedback and improve the model. And there's only so much you can do when you're limited to prompting. So in a lot of cases, I argue that companies today should consider training custom models to power their agents. This would probably not have been a good idea about a year ago, but we've had significant advances in the set of open source models available to us, and also advancements in how we're able to tune those models using reinforcement learning. So here's an example of a company called OpenHands. They're like an open source Devin, not cursor, more windsurf alternative. They started off by building a harness where they were using Claude at the time, but they hooked it up with web browsers to be able to go and look up documentation, edit files, check out your project, run tests, and all that stuff. Once they had that running, they were able to, for fairly cheap, take a model called QWQ, which scores below 20 on SweBench, which was their goal eval, and get that all the way up to 37.2. So I guess the point I'm making is, if you own the model layer, you're able to improve the product when you get customer feedback, and you don't need $5 million to get started training your own model. So all that said, tasks that involve knowledge work are on a trajectory to get solved. I'm really excited to have my lawyer agent charge me $5 an hour instead of whatever they're charging me right now. There's a lot of work that needs to be done to get to that point, but from a just pure what tech needs to be built standpoint, I think we have a lot of clarity. However, when it comes to real-world agents, like agents that interact with physical spaces, there's a lot more unsolved problems, and I'll talk about some of them. When you're building agents, think of, for example, an agent that monitors the security feed and alerts the police if there's suspicious activity. The problem today is visual reasoning is generally pretty hard, and most deployments in the wild are focused on pretty constrained use cases. Things like detect how many cars are in this camera feed or read the license plates, that sort of thing. For real-world agents to be really useful, we need strong vision, audio, reasoning to the level that a human generally can. But with additional constraints, we need them to be able to react in a timely manner. We need them to be reliable and safe under any condition. You don't want your robot falling over and hurting you because your internet went down for a couple of minutes. And if you assume the first two constraints are true, that like agents that interact with the real world need to be fast and local, you also need them to be teachable, because a small model is never going to be generally good at everything. And so you're really, to some extent, you're going to need to customize it. And you can't really do this when you're working with a 70 billion parameter model in the cloud. So let me talk about some of the things we're doing at Moondream. One of the questions you might ask is like, hey, okay, if the model needs to be small and fast, this stuff is probably not ready for prime time, right? Like, it probably sucks as well. Doesn't have to be the case, as this graph shows. Vision AI is still in it's in early days. Like, the blind scaling approach that worked for language models hasn't panned out for VLMs. There's many hypotheses on why this is the case, but our working hypothesis is when it comes to text and reasoning data, there's a lot of it on the internet. But humans, we're just so good at seeing, we don't often write down why we're seeing something. Like, if I look out there, I know that the bird is closer to me than the cranes in the distance, but there's no text on the internet that's paired with images like this that's like, okay, that is a little more blurred, and I see some cloud cover over there, so I think that is further away. That data just doesn't exist in the pre-training corpuses. And I'll talk about a couple more examples of that. So to get really high quality vision accuracy, there's a lot of engineering that goes into it. The blind scaling is not working. This is a chart that shows Moondream's accuracy on counting things. Very common in applications like retail analytics. How many customers are queued up in front of the register? Has this customer been served yet? That sort of thing. Moondream out of the box, on par. Moondream is a 2 billion parameter model, by the way. What that means is it's like really, really, really small. On this vision task, it performs on par with GPT-4o, outperforms Llama Scout, which is 109 billion parameters, 17 activated. Claude Sonnet does currently do better than us, but not for long. One of the things that helped us, like, so there you'll see two bars for Moondream over here. One of the things we did to improve our counting accuracy is, rather than just operating in text space, rather than just asking the model how many people are standing behind the register, we actually ask it to localize those objects of interest in the image. So this little text over here says plus point. And that gives you higher accuracy when there's more than 3 instances of the object you're looking for in the image, which is kind of how humans operate as well. Like, I think up to 3, you'd be like, okay, there's 3 people. Beyond that, you might be like, okay, I see these many people in the crowd over here. Another example of what we do to make Moondream, despite being small, really accurate vision tasks is visual reasoning paired with tool use. So this here is an example from a chart understanding benchmark. The user here asked for the sum of one of the rows in this image. Normally you'd think the answer is 100 because it's a sum of percentages. Turns out that's not the case because of number rounding. It's actually 99. But for this sort of thing, the model can't really just output an answer directly. It needs to be able to reason about it. So we tried training the model to reason, to do chain of thought. And so here you can see that the model actually read the 3 values correctly, 8, 34, and 57 from the chart. But then when it came to adding those numbers together, it completely screwed that up. It said it was like 119. And so over here, you need to recognize that, like, small models have certain limitations. Like, they can extract information fairly accurately, but operating on that information can be challenging. A 2B param model is never really going to get amazing at math. But we found that when we augment with tool use, like if you give the model access to a Python interpreter that it can use on demand, it can very easily write a program that that gives you the correct result. This our original accuracy on this benchmark, when we just like try to do a direct answer, was around 77. No, it was 74. Adding chain of thought took us to 77. It was pretty decent improvement. But giving it access to that Python interpreter took our score then to 82. So you can get a lot of value out of training your model to use to just circumvent things that it is generally bad at. All right, this one. I have a little bit of a story over here. We had this customer sometime in August last year. They were in oil and gas. They had a bunch of wells that were really remote, and they were paying human beings to drive 4 hours out to the wells and take readings on gauges and then report those back. There was poor connectivity over there, so like they couldn't really install a live stream of images that they could monitor. So they reached out asking like, hey, is it possible for us to just like stick a cheap Android phone up there? Like it just takes a photo once an hour, like you process it locally, give us the reading, and we'll text it back or use satellite communication or whatever. I forget the details. I was like, yeah, that sounds like really easy. Check back in 2 weeks. Like we'll fine tune the model to do that for you. Turns out it's incredibly hard. One of the reasons it's hard is because of the same issue, like a similar issue to the one I talked about before. The data we train these models on is just a large set of image text pairs sourced from the internet. It turns out on the internet, if you have a clock, the time on the clock is almost always set to 10:10 because it looks like a smiley face and the watch manufacturers like that. And when you have a gauge, it's almost always a product detail photo that's set to 0. So the models are really good when it comes to gauge question answering. They're really good at telling you like what the brand of the gauge is, what it reads, but the actual like where the dial is, the model pays almost no attention to it. So this turned out to be a much harder problem than we thought. It's also what I call like a multi-hop reasoning problem. It's not something that you can directly, even as a human being, you can't directly figure out what the answer to this is from just looking at the image. You need to be like, okay, I see that the inner dial is Celsius. It's about somewhere between 50 and 55, and that's a reasoning we baked into the model. But in addition to just the text that's output, I have a couple of words that are highlighted. Each one of those is like a grounded word. So in addition to just saying the Celsius label, the model also generates a localization. It's like pointing internally at the image. I count 10 ticks, like it's actually pointing at each tick. And you really need that to get it to be able to do that accurately. So yeah, this was a hard one. It took us about a year to solve it. I posted endless tweets about clocks and gauges on the internet during this time. And now anytime someone posts a picture of a clock, I get tagged by a bunch of people saying, Vik, have you seen this? So those were a couple of things that we do to like really push the accuracy of the model, despite it being at a small size. I want to talk a little bit about performance, as in speed of inference, which is, as we discussed, another really critical thing when you're trying to build real-world agents. Our goal as a company is generally to be in the top left of this graph of like how many resources the model needs to run and like how accurate it is here. Like we plot our performance versus other models of similar sizes on a set of 10 commonly used vision benchmarks. The thing that's interesting here is like that I wanted to point out is like performance isn't just a function of the number of parameters in your model. There's a number of inference time model architecture decisions you make that significantly impact resource usage. So Qwen here is a really good example. Like despite only being 3 billion parameters compared to Moondream's 2B, they need almost 11 gigabytes of VRAM to execute because of some choices they made to boost accuracy. Basically, like they use a massive amount, I think 4,000-ish tokens to represent each image. And that makes it use more memory. It also makes inference slow. There's techniques we do like quantization aware training, which is what this is really showing. So like this and this is basically the same model, just fine-tuned to like perform better when it is quantized, and that cut memory usage in about half lets us have roughly the same memory usage of models a quarter the size. I think we're generally in a good space as far as memory usage is concerned. The next big frontier for us is inference speed. We're doing a bunch of things on that front. Like one of the things we did recently, especially tying back with the reasoning we're doing, like as the model, if you're asking the model to reason, it's producing a lot more tokens. And a lot of people measure performance in tokens per second, which is kind of misleading because everyone uses a different tokenizer. What you really care about is like characters per second or words per second in terms of output speed. So we recently swapped our model to a new tokenizer that's specially designed for like vision reasoning-ish text compression, and that sped up our words per second by about 40%, which is pretty cool. And then finally, any small model is probably not going to be amazing at the specific task that you care about, so these models need to be teachable. We recently did an experiment where, I don't know how many folks here are familiar with GeoGuessr, but basically like it plops you in Google Street View, and you have to guess what country or what specific lat-long coordinate you're at. We did the easier version of it where the model just has to guess which country you're in. Claude 3.7 Sonnet with thinking mode was, I think, the best frontier VLM we found for this. They get 69.1% accuracy. Moondream out of the box was like really terrible at this. We were like 9.9% accuracy. This was a set of 53 countries, so it's basically only slightly better than random guessing. Or maybe it is as good as random guessing. I'll do the math later. Now, historically, fine-tuning was really hard. When we were doing supervised fine-tuning, like you needed a ton of data, hundreds of thousands of images labeled correctly to get good results from the model. And that was blocking a lot of people from being able to do that. Like nobody wants to set up a data annotation team, spend like hundreds of thousands of dollars collecting that data. With recent improvements in how we're tuning these models using reinforcement learning, we're able to get really good results from even doing a reinforcement tuning run on the data constraint graph. There's, I don't have a pointer here, but there's the third one from the left. That was a reinforcement run we did with only 16 images per country and about $2 worth of compute, and that got us to almost the same performance as Claude. And when we use our full data set of around 25,000 images, we were able to significantly exceed the performance of Claude by a decent margin. Now, nobody really cares about GeoGuessr. That wasn't the point of this graph. I think the thing that's really amazing here is it shows that for fairly cheap, both in terms of the amount of data you need and the amount of compute you have to spend, you can take a small open source model and make it really good at your task. And it can adapt to feedback, right? Like as your users are doing thumbs up, thumbs down, etc., like you can actually feed that back into the model. If your product manager comes to you and says like, hey, it's buggy on this output, you can go add it and similar outputs will stop being buggy. You have a lot of control now over how the model operates inside of your product. And so here's an example of the chain of thought the model generates. This is Moondream after we did that reinforcement tuning run for $2. You can see it starts saying like, hey, I see all of these things. I see that the buildings are Dutch or Belgian style. And then down here it says the cobblestone brick streets are characteristic of Belgium or France. And so probably Belgium. And usually gets it right. All right, I'm a little ahead of time over here, but maybe we can take some questions at the end. Just to conclude, a summary of what we talked about, like frontier models will cause you some problems at deployment time. Open models unlock not a lot of enterprise value and allows you to really differentiate at a model level, which is important if it's a core part of your product. Like it makes you better than your competition. Not always the case, like if it's an internal tool, CRM lead enricher or something, like maybe you don't care that much, but if it's a core part of your product, it is something that I argue one should invest in. And then finally, before I take questions, I wanted to leave you with this quote from an essay I read recently that I really enjoyed. It's called Welcome to the Era of Experience, and it talks about how until last year, LLMs were mostly trying to imitate humans. We were trying to train them on massive amounts of data that humans have generated, then train it to match human preferences and responses. With the recent advancements we're seeing, we're in a new era of experience where the models can just try a lot of things out and learn from that, and he argues that that's what's going to get us to superhuman capability, which is interesting if you're trying to build AGI, but I also think it helps us build better businesses in the short run. All right, I think we have about 6 minutes for questions if anyone has any. David?
Yes. Okay, so speaking of learning, thank you very much, Daniel. Speaking of learning from experience, kind of learning on your own, did you have to fine-tune the model to reason in the GeoGuessr game, or did it come up with the structure of reasoning all on its own because that just like maximized performance?
We bootstrapped it with around 200 reasoning traces at the start, and then the rest of it was it learning how to maximize accuracy.
How much did you find did you see any divergence between what you bootstrapped in the reasoning traces and what it figured out was effective?
Yeah, when we don't bootstrap, like the model doesn't, it generates really short reasoning traces, and they're often like, the country is Belgium, and then the final answer is just reformatting it to Belgium because we wanted a direct match over there.
Thanks, Vik. I guess you're responsible after this week.
Fun. Do you think that there's enough sophistication in the generative AI space to get synthetic data for images training, or even some way to take the tokens that you're training on and permute them or warp them into something that you could train on for other kind of variations of the?
We do a lot of work with synthetic data generation, which is part of our secret sauce of why the model is so good. I'll give you an example. When we were doing our reinforcement tuning for gauge reading, this data, like I said, doesn't exist on the internet, and gauges are weird. Like we spent some time going through eBay finding different types of gauges. There's like weird shit going on. Like sometimes like the scale changes from linear to logarithmic halfway through. Like it's just a huge mess, and it's not labeled. So we ended up like writing a little program to synthetically use Blender to render gauges in different configurations. Now we know the ground truth, so we're able to train on that. A lot of the best practices around how to generate and work with synthetic data are unfortunately kept proprietary. So there's a lot of tips and tricks that I don't think the community at large knows about in terms of how to effectively work with it.
Questions? I think.
So when fine-tuning with RL, like, do you include the length of the reasoning traces in your reward function?
Not directly, but the model has a context length limit. So once the reasoning traces start to go over 500, 600 tokens, it starts getting truncated and it learns to go shorter than that.
So just bootstrapping with the RL, like with the reasoning data, is enough for the model to keep generating it during the RL training, right? Thank you.
Yeah, the tooling in the RL space is a little new right now. Like if you're doing reinforcement learning, especially on multimodal, you're very much on the bleeding edge. But it's advancing very quickly. So by the end of this year, like I'd be shocked if it's not very easy for someone to just get started and reinforcement tune their own model.
All right, we have time for one more. I know you were ambitious, but I got to respect the people in the back a little bit.
Thank you for the talk. That was really interesting. Could you talk a little bit about your model choice, 2B parameter model? Have you tried going lower? Like, what are the sort of the trade-off? I might have missed a little bit of that, but.
Yeah, it's 2 billion parameters because the first version of this model was trained on my 3090 rig at home, and that's what fit. It turned out to be a pretty good size. Like it's big enough to where your experiments give you meaningful results in terms of like, will this scale, will this work out, should I throw more money at it? While still being cheap enough that you're able to iterate quickly, do a lot of experiments. But having said that, it is a bit of an awkward size. 2B is like a little too big to really run on edge devices. We do have another variant of the model that's 0.5B parameters. But like the 2B is kind of general, like you can, it'll get you 60, 70, 80% of the way on your problem, and then you can tune it and get really good results. That's not the case with the smaller. The smaller the model, the less effective we found reinforcement learning to be. And so to really deploy a 0.5B or smaller scale model, you need to first train a bigger model to get really good at your task, and then use that to generate a bunch of synthetic data, and then train your really small model. But yes, when it comes to actual edge deployment, especially on phones and cameras and stuff, you probably want to go a lot smaller.
Thank,
All right.
thank you
all
so
very
much. Yeah.
If this was interesting, check out Moondream. Please reach out if you have any more questions.